We've talked about Newton's first law of motion and Newton's second law of motion. And today I'd like to talk about Newton's third law of motion. This is the one that starts off for every action, and then you would repeat, well, there's an equal and opposite reaction. But it's kind of a little bit misleading to talk about action and reaction because sometimes we tend to think one happens first and then the reaction is what happens later. But in reality, in any interaction between two or more objects, these forces come in pairs and they happen simultaneously. As a matter of fact, you can't have one force without having the other force and still have the interaction. So when forces come in pairs, we try to look at Newton's second law and see how does that force affect the object? How does that force cause a change in the object? Remember that that's the acceleration. So let's talk about the interaction between a hammer and a nail. So if we were building something and you had your hammer and you got your nail and you're gonna hit that hammer, or you're gonna hit that nail on the head with a hammer. Well, it turns out that the force on the nail is exactly the same as the force from the nail back on the hammer. Now, it's kind of hard for us to believe. We think, wow, that hammer's so big and the nail is so small. How can you say that the forces on these are equal? But the thing is, we have a hard time seeing force, but we're pretty good at seeing change. Well, that is acceleration. So we can actually see when the hammer hits the nail, we can see the nail accelerate into the wood. And what we don't see is that when the nail hits the hammer has to accelerate too. And it has to accelerate in the direction of that force. Well, when you swing the nail and hit the hammer, what happens on a very small scale is that the force from the nail is actually going to cause the hammer to accelerate. It actually causes the hammer to slow down a bit. It's hard to see and it's hard to notice, but the reason that it's so hard to see and notice is because the acceleration of the hammer is very, very, very small, because the mass of the hammer is very, very big compared to the mass of the nail, which is very, very small. But you see the acceleration of the nail, which is recognizable, fairly large. Let's think about this on a bigger scale. Let's say that you're driving down the road and it's a beautiful evening and you got the windows down in the car and it's summer and you have several friends in the car with you. And as you're driving down the road, all of a sudden, boom, you hit a June bug. Well, it turns out that the force of the bug on the car is exactly equal to, but in an opposite direction, the force of the car on the bug. Like, that's Newton's third law. But we can choose to believe it, or we can kind of look at what happens to the change. I know that force from Newton's second law is mass times acceleration. Well, let's think about the bug. The bug, the force of the bug on the car happens to come from the mass of the bug. The mass of the bug times the acceleration of the bug. The mass of the bug is small. It's very small. But the mass of, or the acceleration of the bug, you see, the bug went from stop to go like he's never, or from go to stop like he's never going to stop again. This would be the bug. But let's talk about how this quantity is the same as the quantity on your car. Well, that has to be equal to the mass of my car times the acceleration of the car. So small you can't even see it. This difference, this change, we recognize the change in the bug. We don't really feel the change in the car. Just like with the hammer and the nail. If you're building something, you swing away at the nail, you don't typically go, whoa, did you see that nail slow my hammer down? Because if you did, you'd probably be building by yourself. And in like matter, if you're driving through the beautiful roads of Swisher in Corinth and a bug hits your windshield, you typically do not exclaim, whoa, did you feel that bug slow my car down? Because if you did, then you would probably end up driving alone. But this is important for us to recognize. We tend to be pretty good about seeing change. That's acceleration. We have a hard time seeing the force. And when two forces hit an object, we say they're equal in strength, but opposite in directions. But the problem also about that is that they're on different objects. Like with the hammer and the nail, one force is on the nail. The other force is on the hammer. Well, you can't cancel a force on a nail with a force on a hammer. Just like you can't cancel a force on a bug with a force on a car. I can only cancel forces on a bug if I have two forces on the bug. You might have seen that in a soccer match. If two people are running to kick a soccer ball and they both swing at the ball with the same force and they both swing at the ball at the same time and they contact the ball at the same time and the ball just sits there going nanny nanny boo boo. And yet the kickers get quite an acceleration in the leg. Lots of force on that leg. The forces on the ball cancel. The forces on the kickers do not cancel. They're on different objects. So we have to look very carefully at Newton's third law and really understand how Newton's second law comes into place when we talk about forces that are equal and opposite.